ROADART is an Horizon 2020 European Union funded project conducted under the umbrella of the Mobility for Growth call associated with cooperative ITS for safe, congestion-free and sustainable mobility. The main research objective of ROADART is to evaluate diversity techniques and antenna concepts in order to develop an in-vehicle platform for cooperative ITS systems for trucks and heavy-duty vehicles. The consortium of the ROADART project consists of 4 prestigious European partners that join their expertise to offer a new vision to the truck-to-truck communications. The 4 partners, including MAN, IMST, University of Piraeus and TNO, collaborated for 3 years in order to provide a viable and reliable ITS solution that will increase driver safety and efficiency and considerably reduce the pollutant emissions and the transportation costs.
MAN brings in know-how from the perspective of a commercial vehicle manufacturer and consequently addresses specific requirements for truck-to-truck communication. The main role of MAN in the ROADART project is the integration of the complete platform in the truck, both on the software side and on the hardware side. This also includes the establishment of a basic infrastructure with the appropriate interfaces that made it possible to develop, apply and test the new communication and localization technologies, as well as this cooperative adaptive cruise controller.
So IMST has 2 major roles in the ROADART project. First of all, IMST has the general management of the project. It leads the consortium activities which include the organization of test and demonstration, evaluation activities, exploitation of the results in standardization fora, bodies, conferences, etc. Aside of the project management activities, IMST is also involved in a technical level within ROADART. IMST contributes know-how in almost all work packages of the project. However, the main task of IMST was the development of the ROADART communication platform, which consists of the necessary RF modules inside the truck side mirrors, the in-cabin communication unit, and the implementation of the ITS G5 communication stack.
The main goals of ROADART was the design and implementation of efficient and reliable multi-antenna communication techniques for truck-to-truck and truck-to-infrastructure applications. The need for efficient communication techniques implies increased data rate and very low latency for safety applications. The requirement for reliability translates to very low error rates and robust wireless communication links among the nodes of the system. In this framework, UPRC proposed, designed and developed innovative communication techniques called diversity techniques combined with pattern reconfigurable antennas. In parallel to this activity, UPRC coordinated extended channel measurements to characterize and understand the peculiarities of the wireless channel. The measurement took place in Munich, in Düsseldorf and in Peloponnesus in Greece. Another important result of ROADART is the development of a geometric stochastic channel model and an ITS G5 simulator that uses the characteristics of the channel along with other dynamic characteristics of the simulated scenario to evaluate the performance of various communication techniques. Moreover, and in order to overcome the non-availability of GPS signals in tunnels, UPRC developed a novel localization algorithm for such environments.
The role of TNO in ROADART is to provide the CICC technology. At the final demo, we presented today a solution which can deal with packet loss, which is much more robust and also way more safe than today's solutions in the market.
The final demonstration of the ROADART project took place in the MAN premises in Munich on the 27th of April 2018. Many people from the main automotive industrial companies and famous research institutions were invited in order to follow a full-day event with oral presentations, discussions, poster sessions, but mainly the final experimental tests of the ROADART platform in MAN's test track, as well as in highways and tunnels.
The novelties incorporated in the ROADART platform cover many areas. First of all is the pattern diversity concept that has been implemented. This concept was made feasible by developing a specific type of reconfigurable antennas called ESPAR antennas. These antennas preserve the useful characteristic of adaptive radiation patterns. Therefore, the system is adapted dynamically to the time-varying environment. The ESPAR antennas are of low complexity and of low cost and are easily located in the side mirrors of the tracks. The Smart RF section cooperates with smart digital algorithms developed in software-defined radios to select and combine the best patterns available each time, and thus provide an efficient and reliable solution. Finally, a novel localization algorithm for environments where there is no navigation system available has been developed, providing high localization accuracy. The algorithm is mainly based on the input from the sensors that are available on the tracks.
The antennas that were designed and implemented for the ROADART platform are electronically switched parasitic array radiators called ESPAR antennas. They consist of a single active and two parasitic printed monopole elements placed in a close distance. The induced strong mutual coupling effects allow us to reconfigure the radiation pattern of the array by tuning the impedances of the parasitic elements with two pin diodes. This specific ESPAR antenna design demonstrates low cost, reduced complexity and compact size. A special switched impedance matching network is also embedded in the antenna design in order to ensure a satisfactory impedance matching for all the operating states of the ESPAR antenna. Therefore, the antenna is able to produce three different patterns, two directive and one omnidirectional. Thus, the employed ESPAR antenna provides the ability to select the most suitable radiation pattern for the corresponding scenario. Two ESPAR antennas are integrated in each side mirror of the track. A special plastic mirror casing was fabricated to offer a solution for the ROADART's final demonstration. The measured S11 responses of the antennas with the mirror casing exhibit an excellent radiation at 5.9 GHz for all antenna states. The ROADART communication platform consists of two RF modules and one communication unit per track. The RF modules are responsible for reception and transmission of track-to-track packets and part of the signal processing. Further processing and routing is done on the communication unit. The RF modules are especially built for the ROADART project around a transceiver chip. A low noise amplifier in combination with short RF coaxial cables results in a very good signal-to-noise ratio. Lower physical layer functions are realized using an FPGA board. The detected packets are then sent to the communication unit via Ethernet for further processing. The communication unit is a high-performance off-the-shelf car PC, and it runs most of the software that includes parts of the RF receiver chain, the diversity engine, the ITS G5 stack, and code to connect to the track network. The localization engine and multiple monitoring tools are also executed on the unit. In ROADART, a novel diversity engine tailor-made for track-to-track and track-to-infrastructure communications was developed. As a concept, diversity is a condition of having or being composed of different elements or qualities. In communications, it is a method for improving the reliability of signal reception with the use of uncorrelated channels that experience different levels of fading and interference. In ROADART, antenna or space diversity was used as the base of the diversity engine. More specifically, the maximum ratio combining scheme was implemented in the communication unit using 4 RF chains. On top of antenna diversity, a beam pattern selection scheme was implemented with the use of reconfigurable antennas. One of the available patterns is omnidirectional for broadcast, multicast transmission or reception. The rest patterns are directive and can improve performance for several applications like CSCC and platooning. Therefore, the developed and demonstrated ROADART diversity scheme is a hybrid space and beam space diversity scheme with the use of ESPAR antennas. 2 antennas were placed into the side mirror casing. The outer antenna produces either omnidirectional or directive patterns looking in front or back with respect to the track axis. The antenna at the inner side produces either omnidirectional or patterns looking in or looking out of the track. With 4 antennas and 3 patterns per antenna, 8-to-1 pattern combinations are possible. In ROADART, 7 modes of operations were implemented: static, without pattern reconfiguration, random pattern selection, random selection with omni support, a geo-tracking geo-networking beam selection, a dynamic reconfiguration scheme for the outer antennas only, a dynamic scheme with Omni support, and a full dynamic reconfiguration scheme for all antennas. In order to monitor, validate, and evaluate the performance of the diversity engine, several key performance indicators were measured or calculated in real time during tests and demonstration. The KPIs were displayed in real time using the visualization web tool Grafana. More specifically, signal-to-noise ratio for ROADART versus conventional V2V transmission, achievable throughput in the available wireless channel, bit error rates where visible peaks indicate failures of the conventional scheme, latency in the leak level measured in the physical layer, the SNR improvement due to the ROADART platform, the packet error rate, and the coverage probability that determines the link availability. One of the developed and demonstrated diversity operation modes is the geo-tracking geo-networking scheme. According to this mode, the patterns are selected based on the relative geometry of vehicles in a given time instance. Through the ROADART localization engine, each vehicle is aware of its position. Moreover, through the received ITS messages, each track is able to know the position of the cooperating vehicle. The engine calculates the relative heading angle between the vehicles, and each vehicle decides on the combination of patterns that best fits the relative geometry of the vehicles. The specific mode can easily be demonstrated in an overtake scenario. In this example, an overtaking maneuver is taking place inside the MAN test track. It can be seen that as the following vehicle overtakes the preceding vehicle, the patterns gradually change from looking front to looking right and then to looking back, tracking the cooperating vehicle. A corresponding pattern reconfiguration takes place to the other vehicle. The geo-tracking algorithm does not provide an optimum solution as far as the radio-related KPIs are concerned, since the radio channel behaves as a random variable with fast fluctuations. However, the geo-tracking algorithm provides significant improvement in the long term with minimum complexity, since the algorithm extracts the patterns through simple geometrical calculations. This video sample presents the behavior of the algorithm during an overtake maneuver that took place in the A55 highway during the ROADART demo. In order to track radio channel fluctuations, 3 dynamic reconfiguration modes were developed, either with Omni support from 1 RF chain per mirror, or with full reconfiguration of all antennas. The engine monitors the SNR and reconfigures the patterns when it falls below a predefined threshold. Reconfiguration is performed in 2 stages to ensure compatibility with the radio standard. The dynamic reconfiguration schemes were presented, tested, and evaluated during the ROADART demonstration event. Throughout the ROADART demonstration event, the transceiver operation was monitored in real time with the use of the Grafana tool, where functional and performance metrics were continuously recorded. Explanation of the presented metrics and quantities was provided to the attendees. In addition, real-time evaluation was performed with KPIs comparing the ROADART diversity engine with conventional communication schemes. A novel localization engine was also developed in ROADART, attempting to improve positioning performance in challenging conditions like tunnels. The localization engine was presented and successfully tested during the demo.
It was to enable and facilitate the use of safety-critical applications in areas with limited GNSS coverage. So, when no GPS exists, we should have safety-critical ITS services provided. But we don't want to be unrealistic, so we could, for example, select a solution that had roadside units and had beacons in the tunnel, so we had many sources of information regarding the location we have.
The localization engine is based on an extended Kalman filter able to operate with variable sampling rates of incoming data from various heterogeneous sources. The localization engine receives data from multiple sources: the GPS, if available, the track sensors, positioning information from cooperating vehicles through ITS services, and openly available map data. The localization result is distributed to interested parties with the use of the DTS protocol. Localization accuracy of 2 meters without GNSS or other infrastructure assistance is a very challenging task. It requires fast update rates and a dead reckoning scheme that fuses data from multiple sensors and exploits publicly available maps. The ROADART engine operated with less than 2 meters accumulated error for a 2 kilometers in-tunnel course during demonstration. In order to monitor the performance of the localization engine in real time, the TrackCar, an open-source GPS tracking platform, was used. The data are sent from the tracks to the servers through an LTE link as soon as new localization results are extracted. It can also be noticed that the update rate is much higher than the GPS measurement rate. That's why the GPS measurement seems to make small jumps when monitored on the map, while the localization engine output runs smoothly. Moreover, in order to reduce errors due to latency, predictive analysis is integrated into the engine functionality. In this segment, a demonstrated tunnel crossing is presented. As the tracks move into the tunnel, the GPS performance gradually deteriorates and finally the GPS stops working. This is presented in the real-time map. GPS measurements stop to update and their respective green marks stop moving. On the other hand, the localization engine continues to operate. The marks representing the localization engine output successfully provide the actual location of the tracks. However, due to the satellite image, it seems like the tracks are moving off-road. The localization engine now produces outputs with the use of sensor data, cooperative communication and map data. As the tracks move to the tunnel exit, it becomes clear that the localization engine follows the highway trajectory accurately and it successfully estimates the time instance when the tracks exit from the tunnel. After a few seconds from the tunnel exit, GPS connection is re-established and the GPS measurements are updated.
We are on the straight part again, and also here we will repeat one time more the acceleration and deceleration in CSC mode. So here you can already see acceleration is increasing by the longitudinal speed. So we are increasing speed for the moment. And you can see the following truck is following that very nicely. And now we start to decelerate for the corner here, and you can see also the following truck is nicely following the speed profile. We're now going to the corner and going into the next round for CSC, where we will show some lateral movements in between the trucks, that the trucks are really robust for the CSC is really robust for the V2V controls, and it's very robust V2V design of ROADART.
First and foremost, the presented ROADART platform is tailor-made for trucks. Certainly, as mentioned previously, we should remain flexible not only with respect to the vehicle type, but also to the employed communication standard. At the moment, there is a lot of discussion going on whether LTE or 5G should be also used for car-to-car applications. On the hardware side, the concept remains the same. That means that the configurable antennas and the RF modules concepts remain also the same. Of course, on the software side, adaptations have to be performed to meet the requirements of the mentioned standards.
The use of advanced driver assistance systems increased over the last years and has not yet come to its end. Cooperative adaptive cruise control is such an advanced driver assistance system that aims to realize automated longitudinal vehicle control while maintaining small inter-vehicle distances. Among other things, a good performance of the system strongly depends on a stable and flexible communication between the operating trucks that can take on different states. However, the communication link of truck-trailer combinations is still to be seen as problematic and critical. due to the large geometry and the resulting shading effects of the radio signals. Distributed antenna systems in combination with beamforming techniques are therefore a good approach to overcome this problem. Of course, CACC might not be the only field of application for this technology. Connected driving in general, such as platooning, cooperative and automated driving, strongly rely on communication and connectivity. That's why the results and the know-how that was generated in the ROADART project will contribute to the development of those automated systems.
I should point out that the whole idea started 3 years ago, and it took 2.5 years from theoretical studies and proofs of concept to the real system that has been implemented in cooperation with the industrial partners and is going to be demonstrated today.
We want to thank the partners in ROADART for their cooperation to make this project into a success.
ROADART project is a success story. The whole thing started with novel ideas and equations on the paper and ended with a real working system on the tracks.